Alright, this is Ken Rosever. So far we've studied doing confidence intervals with a z, we've studied doing it with a t, and we've studied doing confidence intervals for proportions of populations. So each one of these has a important piece of the formula that I want to talk about. This piece right here. You notice that this piece matches on both sides. I call it the arm's reach. And what it actually is the max error of estimate. I'm saying for my guesstimation of mu that because I'm saying it's in this interval, I'm allowing for so much error. You've seen before, maybe in engineering type problems or when they talk about tolerance levels in science, like 5 centimeters plus or minus 0.01 centimeters, or just 5 plus or minus 0.01 centimeters. This right here is the tolerance. And that's kind of how this right here is acting. That's how this right here is acting. That's how this right here is acting. It's the max error of estimate. I'm making an allowance that I'm allowing for this much error, or this much error. Sorry, my pen was not where I thought it was. This much error. It's just like doing tolerances. Okay, I'm tolerating that much error when I say this is my confidence level. So another way of presenting a confidence level is actually, or another way of presenting the confidence interval formula is kind of how you've seen me calculate it. It's x bar plus or minus e, where e is that term right there. That's e. Or down here it's p plus or minus e, where e is this term. And over here it's x bar plus or minus e, where e is this term. Now that error is very interesting because just like you have tolerances in science, where you have like you want to be within 1/100th of a centimeter here, you also have tolerances in statistics where maybe you want to be within 50 cents, or you want to be within, on a proportion, you want to be within 2%. Well, what you can do is you can determine the sample size required so that your estimate will be within your tolerance. And that's what these problems are all about. But before I go on, I'm going to just say to you that you can only do it with these two. And the reason for that is you can take this and you can say, okay, given a e, which is equal to z alpha over 2 times sigma over the square root of n, I can solve for the sample size n by multiplying the square root of n up here and simultaneously dividing both sides by e, and I get this, and then I square both sides, and my formula becomes n equals z alpha over 2 times sigma over e squared. And if I know e, which is my tolerance, my maximum error that I want to allow, I know my confidence level, and I know my standard deviation for the population, I can compute the appropriate sample size, the sample size that I need to come in with this tolerance level for the error. So no more error allowed than that. And also I can do that with this formula here. For the proportion, I can take e equals z alpha over 2 times the square root of p hat q hat over the square root of n, and I can multiply the square root of n up. I can do z alpha over 2 times the square root of p hat and q hat and divide it all by e, and then I can square everything. So let me just scroll down a little. When I square everything, I get n here. I get z alpha over 2 over e. Both of those are squared, and then the squaring eliminates the square root there. and so I end up with that. So I can manipulate that formula to get n by itself. However, I can't do it with this guy. And you might ask why, but the reason is very simple. Every time I change n, t alpha over 2 changes because I go to a different curve. See, there isn't one t distribution. There are many. And so every time I select a new value for n, I select a new curve. And so it's not like these other ones where z alpha over 2 is set. Z alpha over 2, it's set. There's only one possible value for that z alpha over 2 because there's only one curve. But over here, every time I adjust n, I have to adjust t. So this is a much more complicated problem. And so I can't get n by itself really, because t alpha over 2 is also a function of n. Remember, it relies on the degrees of freedom, which is a function of n. So I can't do it with this. You can't do it with that. You can estimate it. If you're doing a t, you can estimate it with a z, but you have to go at least up to a sample size of 30 or greater. Okay. Having said that, you only have these two options then. So the formula for the minimum sample size needed for an interval estimate of the population mean is the one I figured out above. It's right here. It's found on page 362 in your book. You'll use it in your project. You'll use it in ALEKS. And for the formula for the minimum sample size needed for interval estimate of a population proportion is right here. And that formula is found on page 377 in your book. And also they're both listed in the summary on page 391. All right, now let's go and use them. Okay, so let me go here. Hopefully it hasn't logged me out.